This lesson is on Unit 7.2. We're going to be continuing to talk about equilibrium constants, but now we're going to kind of look at what does it mean if you have like a large one or a small one, and then if we have to manipulate equations, what happens to the equilibrium constant. Okay, so to start, let's look at if we have a large or a small k value. So if k is large, meaning greater than 1, the products are favored. So if you recall, when we write our k expression, we have our products over our reactants. Okay, so if our k value, which is basically the ratio between products and reactants, is large, that means that we have a large quantity of products, okay, and a smaller quantity of reactants, okay? So we have favored the products in this case. So if the k value is very large, that means that the reaction goes to completion. Okay, so essentially what this means is it goes to completion is that all the reactants are consumed, okay, and then that's going to produce products, okay? So it's not going to completely use up all of the reactants. That's why all is in quotation marks, okay? But there's going to be very little reactant left over. So it's going to favor the products if we have an extremely large k value. If our k value is small, okay, so again, we have our products over our reactants, it means that we're going to have a small quantity of products and a large quantity of reactants, so that when we divide the small number by the large number, we're going to get a number less than 1. Okay, so in this case, the reactants are favored. So we're going to have more reactants at equilibrium than we do products. If the number is extremely small, like times 10 to the negative 34th, we say that the reaction does not occur. So such a small product is produced that it appears that no reaction actually occurs. Okay, the last thing to note, if k is 1, the amount of products and reactants will be the same, because our ratio, if it's 1, we're going to have the exact same number of products as we do reactants. Okay, so looking at this, we're going to determine which is favored in this case. So we have this equation. We have A gas plus B gas yields AB gas. Okay, so in these particle diagrams, generally what they're wanting you to do is count the particles and plug those in to count as like moles or quantity, concentration of that specific substance. So remember, our k value is going to be our concentration of AB, our products, over the concentration of our reactants. Okay, and our coefficients, we're going to assume that these are balanced. So our coefficients are all 1, so we don't have to raise any of them to a certain power. Okay, so now in order to plug in our numbers, we just have to count how many of each we have. So first we'll start with AB. I have 1, 2, 3, 4, 5, 6, 7, and 8. So I have 8 moles or 8 concentration of that particular gas. So I'm going to have 8. Okay, for my A, it's just the blue dot. I only have 1. Okay, and then for my B, it's the gray dot. I have 2. Okay, so my K value is going to be 4. It's greater than 1, so our products are favored at equilibrium, okay? And just looking at the diagram, we could have kind of guessed at that just because there were a lot more products than there were the reactants in this diagram. Okay, on this slide, it just goes through the different equilibrium constants that we can solve for. We've looked at both the molar concentrations and partial pressures. Just note that there are other ones. We're going to spend a lot more time on our Ka and Kb in a later unit when we talk about acids and bases. Okay, but for this chapter, we're primarily going to be looking at Kc and Kp. Okay, so sometimes we have to manipulate the expression that we're given for our equilibrium constant. So if we flip the equation, we're going to take the reciprocal of the equilibrium constant. So for example, if I have 4NH3 plus 7O2 yields 4NO2 plus 6H2O, and it has a equilibrium constant of 74. Okay, this means that it's going to be favoring the products. If I had to flip this equation so that we're doing the reverse reaction, so that we have 4NO2 plus 6H2O yields 4NH3 plus 7O2. Okay, we're just going to take the reciprocal. So K is equal to 1/74. So in this case, because we're doing the reverse reaction, okay, in our previous one, these were the products, they were favored. Okay, when we reverse the reaction, these are now our products. So in order to show that it's still favoring these species, we're going to take the reciprocal. Okay, so this number is less than 1, so it's saying that it is favoring the now reactants. Okay, if we're multiplying a reaction by a coefficient, we would take the equilibrium constant to that power to get the new constant. So for example, if I have Fe plus SCN yields FeSCN, and it has a constant of 4. Okay, again, this is showing that it is favoring the products. If I were to multiply my whole thing by 2, I would have 2Fe plus 2SCN yields 2FeSCN. Okay, and then I will take my constant to the power of 2 in this case. So my new equilibrium constant is 16. Okay, so it's exponential in terms of our change in our constant. Okay, if we're adding two reactions together, we multiply the equilibrium constants for those reactions to get the new constant. Okay, so these rules are different than what we saw with our thermodynamics problems. Okay, you probably noticed where before when we flipped, we just changed the sign. Okay, when we multiplied, we just multiplied that number by the given number. Okay, and then when we added two reactions together, we just added the numbers together. Okay, in this case, we're going to be multiplying. So if I have, for example, H2 plus ICl yields HI plus HCl, and then we have a K value of 1, or a K1 value. They don't actually give us a real number there. And then we have HI plus ICl yields I2 plus HCl. Okay, and then we combine them. This has a K value of 2, or K2, represents the constant for that equation. We would have H2 plus 2 ICl, because our HIs are going to cancel. And then we're going to have yields 2 HCl plus I2. Okay, so to determine our K for the reactions when combined together, we would take K1 times K2. If they gave us values, we would be able to multiply those together. Okay, so looking at a practice problem on this, consider the reactions below. So we have reaction 1 and we have reaction 2. What would be the expression for the equilibrium constant for the reaction? And they give us this final reaction that we're trying to reach to. Okay, so let's start with our NOBR. Okay, we have 2 moles of our NOBR. So if I look at reaction 1, it's the only one that has the species NOBR. It is on the correct side, it's on the product side, but we do have to multiply this reaction by 2, okay, in order to scale it up. Okay, and then for my other one, so let me go ahead and just write that. So 2NO plus Br2 yields 2NOBR. Okay, and then if we look at our O2, okay, we need O2 on the reactant side, just a single mole. I only have a single mole of O2 in reaction 2, but it is on the product, so I'm going to have to flip this. Okay, so I'm going to have N2 plus O2 yields 2NO. Okay, so our 2NO is going to cancel. So I'm going to be left with my N2 plus O2 plus Br2 yields 2NOBR, which is what I was trying to get to. So that checks out. So now we just have to manipulate our K values. So for this first reaction, because I'm timesing it by 2, I need to square this K constant. Okay, and then for reaction 2, because I flipped it, I need to take the reciprocal. So it's going to become 1 over K2. Okay, and then I need to multiply both of these together. So I'm going to get K2 over, or K1 squared over K2.